And we're live. So how's everybody today? Are you guys ready to do some reverse engineering? And we're live. So how's everybody today? Oh, I have a little bit of an echo. Let me fix this. Are you guys ready to do some reverse engineering? And we're live. So how's everybody today? Oh, I have a little bit of an echo. Should be fixed now. Fix this. Are you guys ready to do some reverse engineering? Whoops. Is it fixed on that? Live. So how's everybody today? Oh, I have a little bit of an echo. Should be fixed now. Okay, now it should be fixed. Okay. Okay, now echo is fixed. Sorry for the technical issue. So yeah, some reverse engineering today. This is what you guys voted for. So we're gonna, dig into this. I hope you had the time to try on your own in order to make, like the most out of this session. Who did try to reverse engineering the Crackme one? The link that I sent. I know that some of you did, like Theodore and Emmanuel did it. They sent me their code. It works very well. So if we have the time, we're going to be able to look at their code at the end after we solve this together. Anyone else did try it? Nobody else? No one else? Okay. Anyone has a little bit of background with assembly? James, you will try after? It's a little bit cheating, but okay. Could not do it. I got cracked instead. Victor? Oh, wow. But going back to what James was saying, that he will try after, I think it's always a good idea when you follow a live stream or you get help from a peer on like any exercise to like really focus on understanding and then do it again on your own without any help. That's how you're going to learn the best, right? Because like every time somebody is going to explain to you, you're going to feel that, okay, I get it, no problem, I can do it. But once you're alone, in front of your whiteboard and in front of your terminal, it's another story. So it's always good to do it on your own to make sure that you actually got everything. And most of the time it's going to be like, you're going to have to do some back and forth. Most of the time you think you understand, but then, you try and you fail, and then you go back, and then you understand better, and then you do it. Godwin, you cracked it, but you had some guide. Great. Lawrence, you got stuck. No problem. Grigory, you get some assembly background. Awesome. Okay. So look, we're gonna try to do an easier one than Crackme one today to start with, and then we're gonna do Crackme one today after this one. And I'm going to try to put myself in your shoes and see how I would have done it if I had like no background in assembly, no background like understanding, the basics. So feel free to ask me any questions on the chat. And I'm gonna try to like go back and forth, like doing this and look at the chat and things like that. So Emmanuel, like the MD5 decryptor that you are referring to this is Crackme 2. So we'll do this maybe in another session. But yes, for Crackme 2, you had to do this. But like, don't tell anyone about the MD5 stuff. It's supposed to be It's supposed to be a secret unless you actually reverse engineer it. Okay, so the first thing we're gonna do is I have prepped for you a very basic Crackme. Okay, and I'm gonna show you the code. And essentially, like if you had to ask for a password, you know, like the most simplest way would be to ask it like from the prompt or like as an argument to your program, and then compare it to the password that you would like to see. Okay, so this is just like a very simple, and don't use this like to secure anything. Like this is like, you're gonna see, it's so easy to crack. But this is basically like a program that takes as an argument the password, and if it's the right one that you know is here, then it's gonna print okay, and if not, then it's gonna ask to try again. Okay, so when we compile this and we run it and we say okay, test, I'm gonna try this password, doesn't work. I'm gonna try any password except the exact one that I have in my program, it's not gonna work. Okay, so let's assume that I don't know the password. Let's assume that this program was sent to me, but I don't have the source code. Okay, I have a question in the chat. So what cohort is this for? Everybody. This is a little bit, so this is covering like some of the tasks that are advanced tasks. And everybody has started C, so everybody had advanced task. This is gonna go through assembly though. A little bit of C, but like mostly assembly. So it's not, again, like those sessions are not mandatory. So if you don't like what you see, if you don't like the topic, you don't have to join. But hopefully you're gonna get something out of it. Okay, so going back to my program. So I've been sent this a.out, program. I don't have the source code and I need to crack it. Okay, so some of the tools that we refer to in the C programming courses, includes, strings, for instance. And strings is a program that's gonna look at a file and list all the strings that it finds in the executable or in the file. So if you run it, you have like a lot of different things. And who can tell me like what these are? Any idea? Nobody? Oh, hidden files. So Remy, you're right that on Linux systems, a file that starts with a dot is a hidden file. But this is not a listing of the directory. This is a list of all the strings that the program strings have found in the a.out program. So these are not hidden files. Yes, these are sections. Correct. Green bell is the first one to have points today. Okay, and we're gonna see like what these are a little bit later, but just like to plant the a little bit of a seed. So you see like different things. You see main also, right? What else can you look at? And then you see like libc. You see here like strcmp, which is the function that we are calling from our program. You see the string try again here. Okay, and right above you see like another string that doesn't seem to be like referring to any library or like section or anything. So let's try this, right? And this is the password. Okay, so this is one way to find passwords for like very bad security program softwares. Um, and this is also like to show you that if you want to ask for a password at one point, you really don't want to do this because all the strings that you're gonna use in your program, well, between double quotes, are gonna be like in clear. They're gonna be in the program, and then just with a simple program like strings, um, you don't see my screen. You should be able to see everything. Can you tell me if you see my screen? You should be seeing like my green prompt. Can you see the green square? You see clearly, yes. Okay. Everybody should, right? I can see. Okay. Okay, awesome. Okay, so with like this simple program called strings, you can get the password so easily. Okay? So let's try to do it like in another way. You know, like as an introduction. We said about, you know, like we looked at this and we said like these are sections, right? But most of you don't know what they are. So let's just like take one and just Google it. Okay, I don't know what they are, what these are. Let's Google it. So I'm gonna go to my browser. Up. And I'm just gonna Google it. This is not jQuery. It's from an executable file. It's not .text, it's text. Okay. So strings, list, text for my executable. Let's see if we can find a reference to .text. Otherwise, we're gonna put like more of them. So let me copy like a bunch of them. Again, I'm trying to put myself in your shoes, guys, in order to like try to solve this. I already know the answers, but okay. So these are like sections, segment sections. So let's put like this word section. The first one we talked about was this one. What is section text in assembly? Okay, so like data, BSS, text, these are like strings that we saw were inside our executable, right? So we have data here, we have text here. What else they were mentioning? BSS. Do we have a BSS somewhere? BSS is right here. And so what they're telling us is the data section is used for declaring initialized data or constants. Okay, great. This data does not change at runtime. You can declare various constant value, file names, or buffer size, etc. in this section. Okay, great. BSS is a section used for declaring variables. Okay, and text is a section used for keeping the actual code. This section must begin with the declaration global start, which tells the kernel where the program execution begins. Okay, so now we know that like inside our executable, we have like different sections and we have a ton of them. So probably what I would do is from there, I would just look at each of those, right? And then at one point, I would hit the one named raw data. Okay, and I would just like put it in my Google. So section raw data. What is this? I don't know. Okay, no. What is raw data section? Let's see. Okay. For an executable program, these are the text section for the code, the data section for global variables, and the raw data section that usually contains constant strings. So wait a second. We know that there's a constant string, which is the password itself in the program, right? So is there a way to look at sections one by one and see what we can see there? And the answer, of course, is yes, there is, right? So one of the tool that you can use is objdump. Oh, sorry, I was on the browser. So let me say this again. So I looked at section raw data. I click the first link. I look for raw data, and I'm here. And I'm learning that the raw data section is usually contains constant strings. And what we have in our program is that the string is encoded into the program. We've seen it with strings, actually, the program strings. And so now what we want to look at is we want to look at a specific section, and we want to look at the raw data section this time, okay? So how do we do this? We're going to use a tool which is called objdump. And we're going to tell the tool to look at, so first of all, you want to disassemble the file, and you want to look at the section.raw data, okay, of the program a.out. And here, what you can see is like this program is going to tell you, okay, what file format is this? So this is an elf. I have no idea what this means, but I'm probably going to Google it just to understand what it is. And then there's a disassembly of the section raw data. And so there's like a number here, and then here I can see the string. I can see this password. I can see the message when you put the right password, and I can see the message when you put the wrong password. So all those strings that were in double quotes, they are in plain text inside the raw data section of the program of the executable. Oh, we have somebody whose name is Amel on the chat. And you are the password. Welcome. So far, do you have any question? No question? Okay. So from there, like I have a ton of questions, right? So the first thing I'm going to do is like, okay, I'm going to Google this. What does that mean? I'm going to want to also like print all the sections and read about sections in executables, etc., etc. One of the things I want to do is, probably because I'm curious, I want to list all the sections inside the program. Okay, so I'm going back to my Google because I have no idea how to do this. You know, I've never done this before. And I'm going to say how to list all sections of a program on Linux. Okay, text, raw data, data, BSS. Display binary object section, size, text, and data. Okay. Okay, and I see here readelf. Sounds interesting, especially when I saw like this elf. Do you remember where we saw it? We just saw it here, right? File format elf. I'm probably gonna need to Google that, right? But going back to my Google, readelf seems like a command that I can maybe use to list all the sections of a program. So the next thing I want to do is I want to learn more about readelf. And there's a man for that, right? So there's a lot of different things. And here I can see that there's an option -s that lists sections. So let's just use it and see if it works. And here we go. Here I have all the sections of my program. This one, this one, this one, this one. And for each of them, I have the size, the type, the address, etc. So while I'm going to take new questions, I'm going to look at the old questions on the chat. So what does the flag -j do in objdump? It helps you select the section you want to disassemble. Canayo, like we already said, it's for everybody. It's not mandatory, so if you don't want to be there, you can leave, no problem. If you want to learn a little bit more about the basics of assembly and the basics of reverse engineering, you can stay, you're more than welcome. How to use strings in the program in safe ways. So Abdi, like if you want to have, if you want to like ask for a password, you never use strings in, plain strings in your program. This is really not the way to do it. And with Crackme 1, you're going to see one way to do it, which is a little bit better, not very secure, but much more secure than this one. Is this really for Core 10? I think, we've already answered that. What if the password is an integer? The password is an integer just if you code it this way. In our case, the password is a string. So if it's an integer, it's going to be like, you're not going to see it with strings and you're not going to see it in raw data. You're going to see it in another way. Probably in the code when we disassemble it. Or all executables like this. On Linux machines, there's like this format is the same everywhere. This is a standard. This is going to be like a little bit different everywhere on different OSs. How did you get the valid passwords? I think we showed like 2 ways to do so far, and we're gonna dig into a third way in a few minutes. No more questions? Okay. Then I'm going to go into looking at the text section. So we saw earlier that the code is in the text section. So let's look at the text section with objdump. We disassemble it, and I'm going to use I like the Intel syntax. There's like different ways of, you're going to see assembly code, right? And there's like different nomenclatures, and I like the Intel one. You can use like, the other one if you want to, but like today we're going to use the Intel one, okay? And I'm going to type less just to look at everything. Okay. So here you have the disassembly of section text. And you look at it a little bit. There's a lot of different things, and see right here you have main. So this is where like, and we know that, there's only this function because we have done the program ourselves, and we can see that there's no call to other functions other than, like library, C library here. But this is essentially like the translation of your C code into the language of the machine. And the language of the machine is actually here, right? And this is like the closest to the language of the machine you can get with the assembly code. Okay? So because we know nothing about assembly, we're gonna need to take a little bit of time to digest, what all of this means. Okay? And so at the end of this, normally you should have looked at everything you need to solve Crackme 1 by yourself without me. Okay? That's the goal. So let's dig into this. So it starts with and BR64. No idea what this means. Let's Google it. Assembly. What does the end BR64 instruction actually do? So this person has like the same instruction, and he's asking like, why is this? What is this? And basically the answer is, and I'm gonna let you Google it and like look into like the details. But this is an instruction that marks a valid jump address from calls and jumps in the program. So when you call a function, you're gonna see this at the very beginning of it on certain programs, not all of them, right? And that's what we see here, here, etc. Okay, and this serves as a kind of a check to see if this is a valid address to jump into. If you call a function and this is not the first opcode, this is not like the first instruction, sorry, then probably something wrong is happening, and then your program is going to be ended and terminated by the OS. Okay, this is true for this program on this computer with this architecture. You don't see this all the time, but this is what we have in front of us. So we're just like learning, the basics of our environment and assembly. Okay, and then we have this set of instruction: push RBP, move RBP RSP, sub RSP 0x10. And I have no idea what it is, so I'm going to Google that. So RBP, RSP, what are these? What is the purpose of the RBP register? Great. Oh, allocating variables on the stack, RBP and RSP. Let's see. It might have to do something with the stack, right? So somebody's trying to learn what this means, and it looks a little bit like us, right? Push RBP, move RSP, RBP, and then you sub RSP a certain number. And what we learn here is that RBP is the frame pointer on an x86 64-bit machine. In your general code, it gets a snapshot of the stack pointer, which is RSP, so that when adjusted or adjustments are made to RSP, reserving space for local variables or pushing values onto the stack, local variables and function pointers are still accessible with a constant offset from RBP. Okay, so we've talked about automatic allocation. We've talked about automatic allocation last week. You know, when we talked about malloc, automatic and dynamic. And the automatic allocation is basically what, you know, like when you have local variables, then your variables are, and the memory associated with them are actually like taken care of by the computer. You don't need to think about it. It's done automatically. Okay? So, and we know that this is basically like those two registers. We learned that those two registers are used to basically allocate variables on the stack. RBP being the base pointer and RSP being the top pointer of the stack. So stack pointer, base pointer for SP and BP. Okay? So if we go back to our terminal, what we see here is like push RBP, okay. You know, we learned that we want to save this value before you change it. That's what, you know, like what we just read has told us. Then we move RSP, the value of RSP into RBP, and then we subtract RSP by 0x10, so 16. Okay, so if we look at this code, I'm going to screenshot this and I'm going to go to my memory template. I'm going to try to see what's happening exactly there. No, isn't working. It was working before. Okay, I'm just going to copy it then. So push RBP, move RBP RSP, and sub RSP 0x10. Okay. Oh, and actually I just need to also, like, because I don't know what those instructions mean, I need to look for them. Push, move, and sub. So let's do that. Push, move, sub, instruction. Okay, get to a guide to the assembly code. So push stack. The push instruction places its operand onto the top of the hardware supported stack in memory. Okay, so I'm going to push RBP onto the stack. So there's the stack somewhere. I'm going to push RBP onto the stack. Let's see for move what it means. Move. Data movement instruction move. The move instruction copies the data item referred to by its second operand into the location referred by its first operand. Okay. So here, when I do move RBP RSP, I'm copying the value held by the RSP into RBP. Okay, so now RBP holds the value of RSP. And that's what we wanted to do, because we wanted to save the value of RSP, the stack pointer, into the base pointer. And then I'm using sub. So let's see what sub does. Sub integer subtraction. So the sub instruction stores in the value of its first operand the result of subtracting the value of its second operand from the value of its first operand. Okay, so basically when I do sub RSP 0x10, I subtract 16 from the value RSP. And 16 is because like this is 0x, so this is hexadecimal. So it's 1 times 16 plus 0, right? So 16. 0x10 equals 16. Okay? So one of the things that I've learned is that normally a stack is, something you put on top of, right? But here you subtract things. Very strange, right? But let's just see like what this means. In memory, I push RBP somewhere into the stack. So let's just say I'm going to push it, I don't know, here. This is going to be my old RBP value if the stack is right here. No. What's the size of RBP? First, I need to learn. The size of RBP. RBP is 8 bytes long. Okay, so I'm gonna need to reserve 8 bytes in memory. So this is gonna take 8 bytes in memory. Let's just say it's here. So I'm gonna push RBP onto the stack. Let's just say the stack is right here. RBP is right here. Okay, and then I move RSP into RBP, and then I subtract, so RSP is right here, and then I subtract RSP, so RBP is a value RBP equals RBP, the value RBP is 48, and then RSP at this point is also 48. Okay, and then I'm going to subtract 10 to RSP. So now RSP is, 15. So RSP is now 32. Okay. So wait a second. RBP, RSP, 32 is right here. So actually, no, it's not working. So RBP is, it's the other way around, right? So RBP is 40 because it goes downwards. And so minus 16, this is 24. Okay. So now I have from here to here of bytes that I can use. RSP point here and RBP points here. Any question? So basically now you have like all this space for you to use for your local variables. Okay? So basically 16 bytes. So let me simplify everything, and we're going to say that from here to here, this is your stack. All of this is the memory reserved on the stack for your local variables for the main function. Okay? So going back to my code, I understood now what this means. And now I'm going to move EDI into RBP minus 4, and I'm going to move RSI into RBP minus 0x10. Okay? Yes, the memory template is right here. It's on the chat. So again, guys, this is for these are like advanced tasks, okay? So we don't expect you to go as fast as I am. I'm just trying to fast forward the way that you could have done it from scratch. But of course, you have to do a little bit more research than I'm doing, because I know exactly where to go because I know the answers already, right? Okay, so now I have those two things. Okay, and let's just say I have no idea what it is. So let me Google that and see if I can find something. Okay. Okay. No. Okay. So here, what does it do? They have exactly the same thing as us, okay? So basically, they reserve space on the stack for our local variables. Then they move onto the stack the values of EDI and RSI. So RBP is base pointer stack, and they don't tell us what it is. Okay. Let's see another one. Where does EDI come from? This is the calling convention. All programming languages for the OS pass the first parameter in RDI. The result value is passed in raxt. Okay, so the first parameter of the function is passed in RDI. What is the first parameter of the main function? What's the first parameter of the main function? Because your C compiler interprets it as 32 bits, only the low 32 bits of RDI and rax are used, which is EDI and EAX. So EDI. What's the first parameter of the main function? Anyone? Are you guys still following me? So David, it's not the name of the program. The name of the program is the first string that you're going to find in the second parameter of the main function. Yes, this is going to be argc. It's the argument count. Okay. So going back here, we're going to push the number of arguments onto the stack at RBP minus 0x4. So, okay. RBP is right here. the value of RBP is right here, is 56 in our example. Minus 4, why minus 4? Why do you think it's minus 4? Anyone? It's an integer, and an integer on a 64-bit machine is 4 bytes. Right? Yes. You got it, guys. Okay. And then the second one is RSI. RSI probably is the second argument, right? So RSI is the pointer to a char. So that's a pointer. So you're gonna need 8 bytes in memory, but you're gonna place this address that is stored in RSI at RBP minus 0x10. RBP minus 0x10 is the beginning of the stack. Because it's a pointer to a char on a 64-bit machine, this is gonna take 4 bytes in memory, 8 bytes in memory, sorry. So this is the address. First argument of the first string. Okay. So now I have my two variables, argument count and argument values. Okay? So this is what it does. And then I'm gonna move what's at the address RBP minus 0x10 into racks. So the register racks now holds what? Any idea? At this point, what does racks hold after this instruction is done? EBP, no. RBP value, no. List of argument. It's not the list of argument, it's the pointer to the list, to the array of arguments. Yes, char star star AV value. Okay. So going back to the browser, now racks holds the address of the arguments. Okay. Now let's go back to the code again. Next line, we add 8 to racks. Okay. So now racks is the address of the arguments plus 8. Why do you think that is? Anyone has an idea? what does Rax hold now? So yes, Gregory, we move the pointer to the next element in the array. So Rax before at that line, at this line, Rax points to the first element of the array. And then we add 8 to get to the second element in the array, because each of those inside the array holds like pointers to strings. Okay, so each of the elements of the array is a pointer. Each of those are like 8 bytes long. So by moving the Rax by 8, you're pointing not to the address of the first element, but the second element, which is actually the first argument to the program. Okay? So now here, Rax holds the pointer to the string. Okay? And now you're going to move the pointer, the address of the string, into Rax with this instruction. Okay, so now Rax at this stage address of the string, first argument of the program. Okay. Just making it clear. Got it? Okay. So going back to the terminal, now we have like this instruction. We load rip plus a number into RSI. And then let's just do this one. So I have no idea what this means, right? So what is rip? Let's Google it. Yeah, I guess I need a little bit more. Rip. Okay. Rip register. Maybe it was like a documentation about registers in assembly 64. I don't have rip here, of course. The role of the rip register. The rip register on x86-64 is a special purpose register that always holds the memory address of the next instruction to execute in the program's code segment. Okay? So this is basically like it always points to the next instruction to execute. So if we go back to the code, the address of the next instruction to execute at this point is 118E. And you add E76 to it. Let's do the addition. 118E plus E76. Already prepared that for you. So the result is like 2004 in hexadecimal, okay? So what is at this address? And if you go down, it's not code, right? But you remember that we have like other sections, and one of the sections that we have is the raw data section. So what is at the address 2004? This is 2000, 2001, 2002, 2003, 2004. This is this text. Okay, so probably at this point, you're gonna test the program with this password. But let's just say you're not curious enough, so you're just gonna continue to look at the assembly code. But basically this is like the address 2004 resides the string AML, which is your password. So you load the address of the password into RSI, and then you load racks, you move racks into RDI. RDI now contains the argument that you passed to your program, so your password. And then you're calling strcmp, and you know that strcmp is a function that is used to compare two strings. So you're basically comparing the first argument that you passed to this one. And then you test the result, and if they're not, then you test the result. But essentially at this point, you know what the password is. Okay? So I'm going to do a small pause here before we get into the rest of the code to take questions. Okay, so we code Africa, you have a question. Does the address of the string overwrite rack's value? The address of the string overwrites rack's value. You mean here? When you move racks, qword ptr racks? Yes, every time you put something into a register, it deletes what was there before. So it overwrites what was held by racks before. Any other question? Okay. Are you guys still with me? You guys following? The spreadsheet is a Google Doc, yeah. Let me put the link again on the chat. So Omojola, apart from the raw data, how else can we locate or see the content of the specific address? So like the specific address is this, and you remember with readelf, you saw like at which address starts each section. So you look at this table, and then you're gonna see in which section you want to look into. We code Africa. Which architecture should I learn to dive deep for reverse engineering? The one you want, doesn't matter. And Guji, I read somewhere that stack and heap grows in opposite direction. Do you mind explaining this? I think it would help understand the position of the RSP and RBP. Yeah, sure, no problem. So let's do a little bit of whiteboarding. Okay, so basically when your program is loaded into memory, the OS like creates like a virtual memory for it, for your process. Okay. And here you're gonna have like a lot of different things. You're gonna have the, you know, the arguments that are passed, int rc rv, etc., etc. And then at one point you're gonna have the stack. The stack, let's just say, is gonna start here, right? And then when you reserve space on the stack, it grows that way. And that's why you do like sub rsp 0x10. If it were to grow that way, the other way, you would have to like move RSP up. Okay? And then here you're gonna have your executable, and then, you know, with all your sections, and then somewhere you're gonna have the heap, and the heap grows this way. So every time you call malloc, and when you do, the OS has to reserve space for it. It's not all the time. It's a little bit more complicated than that. Then the OS grows the heap that way. So like these are like addresses that are going to be returned by malloc are going to be way smaller than addresses that of your local variables on the stack. Okay. Wi-Fi passwords also somehow uses this format. I see. No. Like this example of like asking for a password and checking for it is the most basic you can think of. If like all the programs were done this way, then, you know, everybody would be hacked all the time. So it's much more complicated than that. Can the manual steps be automated? David, I don't understand your question. Which resources would you recommend for learning more about Intel assembly and reverse engineering? I have like a few books I can recommend. I don't remember exactly the names of them, so I'll tweet them later on today or tomorrow. You mean you can use Node and Python or Rust for reverse engineering? You can. I would recommend to start with like, you know, like the very low level languages, you know, with C stuff. It's a little bit more easy to understand because there's a lot of things happening with higher level programming languages. And actually like most of the Python versions are like C Python. So like Python under the hood is written in C, right? For most of the version of Python. So like it's good to like, you know, look at a little bit of assembly from like disassembling like C stuff, and then you can, you know, move your way up from there. And there's a lot of different things like Windows and you know, different OSs, like they work differently too. So try to focus on one OS first, and then like move up. And once you understand everything about Linux, then you can move to Windows and you can move to Mac, etc. Does memory allocation prevent buffer overflow as compared to the stack, and when do you use both? No, malloc does not prevent for memory allocations from buffer overflows. And the stack sometimes does, sometimes does not. In this example, there's no check, but there are like other programs, and we'll see later, that creates like some kind of a token and put it on the stack. And every time you clean the stack, when you exit a function, then it's going to check for this token but the token is right there at this address and has not been overwritten, to check for buffer overflows. The malloc has like also like the heap. Normally the heap, like in theory, starts where the executable ends and then grows from there, because the heap is like the end of the executable. But like there's also like on like modern OSs, like there's like a small gap that is random between the code and the heap, in order to like try to not get the overflow the other way around. Like I don't want to get into like too much specifics. I just want to make sure that everybody understands the very basics before we move on to the next instructions. It would be helpful to have a memo for all the steps for this task, Joshua. This is a great idea. If you can like write a memo and share with everybody on Twitter, I'll retweet. Okay, all right. Let's go back to the code. So how do we reverse engineer GUI applications like CorelDRAW? Like same principles, but much harder, because like, you know, like the as we go through time, there's like more and more ways to secure your program so that it's not hacked. Because like as an editor of a program, you don't want your program to be hacked, right? So you want to make sure that you have like all the security that are in place. There's like so many ways. You know, this is just step 0. Again, I don't want to get into like a rabbit hole here. Let's just like focus on like the first one, and then you know we will grow from there. So let's move on. Pablo, hey guys, just hopped on. What are we talking about? Yeah, it's been an hour, so I invite you to restart the video from the beginning. But this is basically reverse engineering like a small program. Okay, so let's go back. So we understood everything until here. Now we're gonna test EAX and EAX. Basically, we're gonna test that EAX is 0, because when strcmp returns 0, it means that the two strings are the same. And if they are not equal, then you jump. GNE is jump if not equal there at 11A8. 11A8 is this here. You load what's at the address. You load the address RIP plus E61. RIP, we saw that it holds the address of the next instruction. So 11AF plus E61, and the result is 2010. Okay, if we look at, we know that raw data starts at 2000, 2010 is this. So if it's not equal, it's going to print the string try again. Okay, otherwise it's going to load RIP plus E6B. RIP is pointing to the next instruction to execute, so 11A1 plus E6B, that is 2000C, and 2000C is here, and it's going to print OK. So you call put s, which is like putting, you know, put string. So it's like printing a string on the terminal. And then you leave and you return from the function. Oh, and this one is you put 0 into EAX and then you return the function. You remember, main returns 0 if everything goes well. Okay? Any additional question before we move on to the Crackme 1? In the Crackme 1, I'm going to go a little bit faster because we've seen the basics. So please ask your questions right now. There's no bad question. Anyone? Yes, Dira, I will recommend an assembly book. I have like a few in mind, but I just want to make sure that I have the right names. So I'll put that on Twitter. Oh, David is asking like, can we brute force this program? Yes, you can. It's gonna take a lot of time, but in theory you can. Okay, no more question. Let's go to Crackme 1. Do you guys want a break, or should we 5-minute break, or should we go right away into it? Oh, the raw data instruction. So you're gonna. So the question is like, how do you see the raw data instruction? The raw data segment, not instruction. Boundary, okay. So I'm using objdump, and instead of the text section, I'm just like putting the raw data. Okay. Okay, so you guys want to go straight into Crackme 1. So let's do Crackme 1. So let me run it. Okay, access denied. Access denied. Okay. So let me try to find, with the basic tools, can I find the password? So these are my segments, sections, sorry. There's like access granted here. There's like, what else? Access denied. But I don't see like a string that looks like a password, right? So let's just check raw data just to make sure. Access deny. Oh, Jenny and Jen love ISM. Let's try this. Ah. What's wrong? I've copied everything. It's not working. It's not working. Doesn't seem to be working. Right, so it's not this. Can we see like something else? Might be this big number as a string, maybe. Let's try it. So I'm just copying everything into one buffer. Okay. Oh, actually, this is not the one that we wanted to do. Sorry, guys. This is this one that is the simplest. Okay. Okay, let's forget about it. We're gonna do the same thing. So Crackme, we're gonna test. One password, what happens if I put 2? Tells me I need to have only one argument. Okay. Okay, so let's do strings on the program. Do I see anything that looks like potentially a password? I see this. This is the error message when I pass 0 or more than one argument. Wrong password is the message that is shown to me when I put the wrong password, and tada congrats is probably the string that I'm gonna see if I manage to find the password. Probably my program is gonna use putS, printf, but I can't see anything that looks like a password. Let's check raw data. So by the way, this was the one that I told you guys to try before coming in. So I can see my string usage, password, wrong password, tada, congrats. It's probably not tada, congrats, but just to make sure, let's try. Oh, come on. Tada, congrats. Yeah, it doesn't work. Okay, so it doesn't seem to work like, you know, the first one, which was like, we know very basics, and, you know, probably you're not gonna see a lot of those that are like that easy. So it's gonna be something else. So there's like many ways to solve this one, but we're gonna do it with the tools we know. And so we're gonna use objdump. So objdump, and we're gonna look at the code, which is in the text section. Right? Now we know that. I'm gonna pipe it to less. So let's try to find main. So I'm seeing main, and right above, I'm seeing a function that is called checksum. Interesting, right? Let's just imagine we haven't seen this, but it's probably a clue for you to understand this. But let's examine the main function, because, you know, the program starts with main. So look, we have push RBP, move RBP RSP, sub RSP 0x20. Looks a lot like, you know, a lot of the functions you're going to see in assembly. So you're saving the value of the base pointer, you're moving the stack pointer into the base pointer register, and then you subtract 0x20 to RSP. So on the stack, for the local variables, you have reserved now 0x20 bytes, so 32 bytes of space for your local variables. You're moving EDI at the address RBP -014, and you know that this, from the previous exercise, you know that this is the number of arguments. You're moving RSI into RBP 0x20, okay, on the stack. And from the previous exercise, you know that this is the pointer to the array of arguments, and which each argument is a string. And then you're comparing. So like from there, like everything we've seen already, right? So there should be no question, okay? But if you do, please ask on the chat. So the next one is you're comparing what's on the stack at RBP -14 with 2. And then if it's equal, if what's on the stack, so the number of arguments, you know, is at RBP 0x14. If the number of arguments, and remember, the first argument in the array is the name of the program. So if you have passed basically one argument to your program, then you jump to 4005D2, and 4005D2 is right here. Okay? Otherwise, probably what's gonna happen is that you're gonna basically print the usage, right? Let's check that. So if not, then you move RBP minus 20 into racks. You move what's at racks into racks. So here is the array of arguments. This is the first argument. And then you move the address of the first argument into racks. You move it into RSI. And then you move this into EDI. You move 0 into EAX, and then you printf. And essentially what you're printing is usage, the name of the program, which is in which is the first argument, which is the first element of the array of arguments, and then you printing the rest. Okay? We're not gonna like go into the details, but that's what it does. So, but if the number of arguments were the correct ones, if you have like 2 arguments, so you passed 1 argument to the program, then you go to 4005D2. 4005D2 is right here. So now what do? You move what's at the stack at RBP minus 0x20. This is the array, this is the address of the array of arguments into racks. You add 8 to racks, just like last time. In order to do what? In order to take the argument that you passed to your program. You know that you have an argument there because you just checked that you had 2 arguments to the main function. Okay? 2 arguments into 2 arguments in the array of arguments. You move it, so now our racks points to the second element of the array, which is the argument that you pass to your program. And then you move these strings into racks, you move racks into RDI. So now RDI contains the string that you passed as an argument. Okay? And now I'm going to call checksum. So I'm calling checksum, and at that stage, at that point, RDI points to the string that you passed as an argument. Okay? Any question? Let me know if you need me to repeat like this last portion. Any question? No question? No question? Type no question if you have no question. Okay, Angelique, I'm gonna repeat the last section. So we said that if I passed a password and only one, then I'm gonna jump into this address right here. Here I'm moving into racks the pointer to the array. So now racks points to the beginning of the array, so to the first element of the array. I'm adding, because RBP minus 0x20 holds the array from this instruction here. Okay? I'm adding 8 to racks. So it points to the first element of the array, and now I'm adding 8 to this address. And so now it points to the second element of the array, because the array holds pointers, and each pointer on a 64-bit machine is 8 byte long. So now I'm pointing to the second element of the array. The first element of the array, argv, is the name of the program. The second one from the command line, and the second one is the first argument that you pass to the program. Okay, so this is essentially the password that you're trying to test, that you passed on from the command line. Okay, and now you're moving the pointer to the string into racks, and then you're moving racks into RDI, and then you call checksum. So when you're calling checksum, we need to remember that RDI holds the address of the string that you passed as an argument to the program. Got it? And yes, this is the address of the function checksum, 400,566. So if you go above to find 400,566, this is where checksum starts. So Reinhard, we've seen this like in depth like an hour ago. This is basically like reserving space on the stack for local variables. So here, what does it do? It starts with pushing RBP, move RBP RSP, and then it doesn't seem that it needs any variable, right? It doesn't reserve space here. But here, we're gonna put RDI into RBP minus 0x18. So RDI, remember, holds the address of the string, of the password that you are testing when you run the program. So now here we have the string, and here we have 0. Okay. So now what's happening? What's happening is that you're jumping into 40058C right away with no condition. And so here, I'm going to do it step by step with the memory just to make sure that we are following. Up. So let me see if I can put that into here. So I'm gonna share my whiteboard. Okay. So we have RDI is the string address, you know, your password address. Okay, we have RBP minus 18, 0x18 is the password. Okay, and we have RBP minus 8, which is 0. Okay, at this point. Then what we say is that we jump right away to 40058C, which is here. So here you're moving RBP minus 18 into racks. And then you move the byte at the address racks into EAX. Okay? So let's just do it step by step. For the first time, we're going to take a little bit of time, and then we're going to go a little bit faster. Okay? So right here, you're moving 0x18. So this is the address of the string into racks. So racks holds the address of the string. Now you take what is at the address of the string, you take 1 byte, and you move it into EAX. So EAX now holds the value of the byte that was pointed by racks. So essentially the ASCII code of the first letter of the string that you passed as an argument to your program. And then you test if this byte is 0. You test if those are 0. Okay, so why do we do this? Probably you're going into some kind of a loop and you're testing for the \0 byte. Okay, if they are not equal, then you jump to 400578. 400578 is here, and so here you're moving the byte into racks. You move the pointer to racks, the address of the string into racks. You move the byte pointed by racks into EAX, and then you move AL, which is the byte of EAX, because EAX is 4 bytes long. You move it into racks, and then you add racks into RBP minus 8. Essentially what you've done is that racks now holds the ASCII value of the letter, at that point the first letter, and you add it to RBP minus 08. So now RBP minus 08 is 0 plus ASCII code of the first letter. Okay. Then what you do is that you add 1 to what is at RBP 0x18. 0x18 was the address to your password. So if your password was test, this was pointed to the first letter. And now you're adding 1. So now this points to the second letter. Okay. Now you move what is at. So now basically you redo everything that we just said. So this is like the 40058C that we started with from this jump. Okay. So same thing here. You take the address, you put it in racks. In racks, you take what's at racks, you take 1 byte, and you put it to EAX. So basically now EAX holds the value of the ASCII value of the letter E in our example. Then you test that it's not 0. Because it's not 0, you're going to 400578 here, and you do everything again. So you're taking this pointer, you put it into racks, you put what at the address racks into EAX. Now EAX holds the value, the ASCII value of the byte. You move this value into racks. Racks is added to RBP 0x8, which now holds 0 plus the ASCII code of T plus the ASCII code now of E. And then you move the pointer by 1, and you do it again and again and again and again and again until here you hit the \0. Okay? So remember, at the end of each string in C, you have a \0. The ASCII code is 0. So if it is 0, then jump if not equal is not going to be, you're not going to jump into doing the loop again. Then you're going to do move RBP 0x8, so basically the checksum into racks, and then you return. So basically what does this function do? It adds all ASCII letter values. Okay, and then at the end, it stores it in racks and then go back to main. And in racks, you have what you call the checksum. Okay? Any question? Yes, Bongo, it's a loop. And that's one way of doing that in assembly. So from the C code, this is how it's translated. There's like different ways to do this, but yes, this is a loop. Any question? No question? Okay, so we're going back to main. You ready? So remember, racks contains the sum of all the ASCII values of the letters of the password that you passed as an argument to your program. Okay, so going back to the terminal, we called checksum. Now we return to main. So Angelique, so the ASCII code will tell us the password. So like the sum of the ASCII code needs to be like, it's going to be checked against something to know if the password works or not. Okay? So going back to the main, it calls checksum here. And remember, at the end of checksum, racks contains the checksum. And then you put racks into RBP minus 8, and then you compare RBP minus x with 0xAD4. Okay, let's write this down. 0xAD4. If they are equal, then you jump to 400C604. Right here. Then you move this into EDI, and then you call put S. So what is this? 4006C7. Is it here? Probably not. Could it be in the raw data section? Yes. And so C7, 0, 1, 2, 3, 4, 5, 6, 7. Ding, 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 ta-da, congrats. Okay, so essentially, if what we just saw is that if the checksum is 0xAD4, then we win. And the rest is just like saying like, try again. Okay, so in order to find a password for this, in order to create a password, you have to create a password which sum of its ASCII value for each of those letters adds up to AD4. Okay? Is it clear for everybody that this is what it does? Any question? No question? Does that mean the password will work in any other? In any other? Yes. It means that like this can work with a lot of different passwords as long as the sum of its ASCII value letters is 0xAD4. Okay? Yes, Samuel. There could be more than one. You are correct. Yes, Bongwe. Yes, David. There are many different combinations that work. This is not one password. It's, a lot of different passwords that could work. And like 10 years ago, a lot of the softwares were asking you for some kind of like password or like license number or things like this. These were different from one person to the other, but like the actual software was just checking against some kind of a combination of a checksum and other things. That's how like they created like different like strings, but for one software which was not connected to the internet to check the password. Do hackers use this? All the tools that we are using, yes, hackers are using them. Okay, so now the goal is to create a program that generates a random key so that it's going to work with my software. And this is called a key generator. Okay? And so it's, already like use an hour and 45 minutes. So what I'm going to do is I'm going to show you the work of Theodore and Emmanuel, who have been working on this. And it took them somewhere, probably I would guess like 12 hours to do everything. I don't know if you guys are here, is that correct? Let me find, where is it? So Belak, this is the checksum that you need to get to have the right password. So Uche is asking like, how do we get ASCII values that add to 0xAD4? This is exactly what we're going to show if my browser is okay to work. There's different ways of doing this, but I'm going to show you the code of... Oh. Sorry, my computer is lagging a lot. It's very, very slow. Yeah, it took them 6 hours plus a day. So let's just call it 16 hours. 16 hours to do everything. So again, like when you start from 0, it's going to take a little bit more time that me, even though like I started with a lot of questions on Google and things like that, because I know where to go, right? So It's a lot of whiteboarding, it's a lot of Googling, it's a lot of reading to get to understand like what the program does. Where is everything? My computer is in the process of crashing. Okay, so this is the code of Theodore and Emmanuel. And I'm just going to comment this. And then guys, if you want to tweet a little bit about how you did this, and if you want to write a little bit, of all the steps that, you used to get to the end result, please share with everybody and ping me and I retweet, so that you can see that you can see like all the work that has to be put into this. I'm using the wrong window, of course. Okay. So one way to generate the password is to basically like start with random pass. You basically have like a set of letters that they have defined here. And then here, what they're going to do is that they're going to randomize the number of the letter that they're going to add to the string. And once it hits this number, which is the 0x84 that we saw earlier. This 0x84 is in base 16 and 2772 is in base 10. They could have put 0x84 here instead of 2772. It's the same thing, right? But essentially, like while the key is less than, you're gonna add a new character, and then you're gonna take the ASCII value of the character, and then you're gonna add it to the key. And then you add on top of this, etc., etc. And then at the end, when you're done and you find the exact key, then you add the \0 and then you print it. So if I take this code and I use it here, come on, hello, okay, emacs keygen.c, okay, so this is one password, this is another one, no. And then I try this. Oh, it doesn't work. Ah, it doesn't work. It doesn't work. I tested this yesterday, guys, and this morning, I mean, it was working. Did you change anything? It doesn't seem to work anymore. So it works, but like not always. But you understand the principles against it, right? You basically randomize like each of the letter that you're gonna add to the key until you get there. Once you have this, then you print it. Yeah, on Modular, this is another way to do this. You can like start with like one specific letter, add it, like many times, and then you add like any extra character that make it up. Denzel, your mind is flying. It's good. Okay. So this is the end of the live coding. What did you guys think about it? Do you think it's like, it was too hard? Do you like it? Do you want more like this? Or do you prefer like me to focus on like the basics of C and pointers? What do you guys think? Did you learn anything? Was it entertaining? Oh, how do you make the password string invisible in text or raw data section when you write the program in C? There's like many ways. Like the best is like not to use a string at all. But you could think about like a very simple way. For instance, Samuel, you could do like you have a string and then you modify it when you run the program, and then you test again the modified string. So for instance, if you had something like like char password equal hello world, and then you do like at one point you say, okay, password of 2 equals x, and then you check against password after you modified it. That's again, very basics, very naive, but you won't see the password in the raw data section normally, unless the compiler is optimizing without telling you. It happens sometimes, but probably like this you won't see it. We can test it right away if you want. Even like just something very simple. Okay, you have the password, you modify the password, and if av1 equals, no, if strcmp of av1 and passwords equals 0, they are the same. And else printf, try again. Return 0. Okay, normally you want to really like check like if, let's say that if AC equals 2, and just to make sure you're not going to crash if nothing is passed, then gcc main to you call it Crackme. What? Oh. Okay, if no. Okay. strcmp. Okay, man, strcmp. You need to include string.h. Okay. Printf, man, printf. Include stdio.h. Okay. All right. So Crackme, try again, test. Okay. And so now if you do strings of Crackme, the password. Is it this? That was our password, right? Hello world. Okay. You don't see it really, like, you know, with the X. And then if you do raw data, dun, 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 raw data of Crackme. Here you have, okay, try again. Okay, so this is like one of the cases where you don't have everything. You know, you don't see it basically. But it might be like one of the case where the compiler is optimizing and then your string is actually compiled as a number. Let's just check. Yeah, here this is like the this is your string. This is part of your string. This is the end of the string. So there's like many ways the compiler is going to optimize your string. I don't want to get into like too many details, like this getting like a little bit more complicated. And also like I need to explain the little Indian versus like big Indian thing if I want to get into this, and it's going to take an hour. So this is one way of doing this. You don't see the string. Okay, so yeah, so basically some are telling me you want more like this, more advanced, but others are telling me more basics. Okay, Acid Hug, like feel free to check all the previous live coding sessions. They were all about the basics of C. So let me know if you find any value there. Theodore, more weekly sessions. I'm trying as much as I can. I don't know if I can do this all the time. I have a lot of things to do at the same time, so I'll do this as you know, as anytime I can do it, I will do it. But I can't do this every week. It's not possible. Thanks, Uche. The strings from the keygen are like 8 characters long, even at an average ASCII value of 150. How do they add up to 2772? Yeah, so Omo Jola, the only strings you saw were the strings that did not work. So the real strings that worked, they were like in back quotes, and so we didn't see them. But yes, they are longer. You're right. I won't forget about the books. I have one in particular that I really liked when I started learning about assembly. I'm going to try to find it out. How do we get previous live sessions? So you're on YouTube right now, and you just go to my channel, and you're going to see the list of everything. Let me put it in the chat, the link. All right. So this is the link of the channel. So yeah, make sure you subscribe, and then you have the alert button. So every time I'm going to be online, then you're going to receive an alert. Okay, guys, that's it for today. It's been 2 hours. It was a pleasure. Like send me like more questions on Twitter if you want to. You have my Twitter handle like right on top of my head. And I'll see you guys later. Have a good day, have a good night, depending on where you are in the world. Goodbye.